Hey friends, MoNaCo here. Your fourth lecture note on organic chemistry. We're going over concept of isomers today. Isomers are it's a term that applies to organic chemical nomenclature. Basically, as hydrocarbon chains get longer and longer, there's more and more ways for them to be arranged. Okay, so an isomer is technically two molecules that have the same, how do we want to say this, molecular formula, but different structural formulas. So it's a Lego castle made out of all the same Lego blocks, but my castle versus your castle might look radically different. Has all the same blocks, all the same pieces in the same kit, but the way I put my castle together is different the way that you put your castle together. So, is there really more than one way an organic compound can come together? And the answer is yes. Organic compounds are like puzzles. When connecting carbon atoms together, there are many different ways to connect the atoms. If you're given a chemical formula like C4H10, there's actually more than one way to connect the atoms to make molecules. We chemists call these alternative structures isomers. They're two chemical compounds that have the same molecular formula, but different structural formulas. For example, just from that C4H10, well, I could make the carbon go in 4 straight chains and fill up with all the hydrogens around after I'm done. Okay, so this is one version of C4H10. Now, here's another version of C4H10. I do a 3-carbon chain with a 1-carbon branch, and then I fill up everything else with the hydrogens. If you count, it has the same number of carbons, same number of hydrogens. It's just that the shape is actually different. So while it might be the same formula, these two molecules would not react exactly the same. We call them isomers. That's the point of this lecture. Compounds that have the same molecular formula but different structural formulas and different names are isomers. They have different chemical and physical properties. At least 4 carbons must be present in a molecule to have a potential isomer. So isomers only kick in after you've got a carbon chain that's larger than 4. For example, 1 carbon here, there's no way to rearrange that. There's only one way. Ethane, you flip it forward, backward, side to side, it's the same. This one here, 3 carbons, propane, because they're all single bonds. Also, there's no way to make an isomer of propane. But butane, having 4 carbons, is the first example of a isomerizable chemical compound. So there's only 3 ways to make an isomer. You either make a branch, you move a branch, or you move a multiple bond, like a double or a triple bond. For example, N-butene versus 2-butene. N-butene is that way. 2-butene would be this one. You see, they're actually different molecules. Once I fill them up with hydrogen, they're actually going to be different molecules. Even though there's butenes, we just moved the double bond. That was one example. Or moving a branch, which is what I did in the first page of this particular notes. Moving a branch is kind of like this. If I don't have a branch, oopsies, there we go. But if I do make a branch, I've moved it. I moved a carbon to become a branch. I'm sorry, that was making a branch. I could move a branch, for example, doing something like this. If I had methyl pentane. See, so I got a carbon backbone of 5. If I had, this would be 2-methyl pentane versus 5 carbons, 3-methyl pentane. Same formula, branches in a different spot. So it's different molecule. Same formula, different molecule. That's what's tough to understand about isomers. Different molecule, different behavior. Here's some pentane isomers. They break off a terminal carbon and put it in a non-terminal position. So terminal means at the end. Basically, pentane, N-pentane, normal pentane, looks like a straight chain. 2-methylbutane. Uh-oh, scary. What they've done here is they took this carbon and just slapped it onto the second one. Okay, so instead, the methyl group hangs off the second carbon. The longest chain is 4 instead of 5, so we name it butane. It still has the formula C5H12. C, 1, 2, 3, 4, 5, C5H3, 6, 9, 12. But it's called something different. C5H12. It's not the same molecule. It's the same formula, not the same molecule. Dimethylpropane. Well, we count the carbons. I got 5 carbons. Count the hydrogens. I got 3, 6, 9, 12 hydrogens as well. Yet the name is something completely different. And the structures are not equal. So these are not equal when we're talking about it. The formulas are, but the structures and the way these molecules go together are not. And therefore, they behave differently in our bodies and in our environment and our world around us. You can only make branches on non-terminal carbons. Again, terminal carbons are at the end. So you can either make a branch, move a branch, or move where the double bond is, or the triple bond is, to make an isomer. You cannot change the formula. You can only change how the puzzle pieces, the atoms that is, go together. So pentene isomers either break off a terminal carbon and put it in a non-terminal position or move the double bond. So let's start with N-pentene. Pent, 5 carbons, ene, double bond. So we're going to have a double bond between a couple of carbons and 5 carbons in the chain. So we're going to start with 5 carbon chain, and we'll put the double bond between the first 2 carbons, and we'll fill up the rest with hydrogens. The reason why we created molecular formulas is because all this drawing got some of us chemists upset. So this is N-pentene. N-pentene. So you could break off the terminal carbon and put it in as a non-terminal position, meaning make a branch, or we can move the double bond. Let's start with moving the double bond. Let's do the next carbon straight chain. 5 carbons in the chain. But instead of putting the double bond on the terminal carbon, we'll put it between the second and third. We'll fill everything else up with hydrogen. And this is not N-pentene, but it is 1,2-pentene. So there's 3 other isomers that we're going to have to approach here. If I move the carbon double bond again, one more spot down the line, it's going to be a mirror image. So it's not actually going to be 3-pentene. It'll be the same as 2-pentene. So I can't move the double bond anymore. I'm going to move on to branching things. So instead of putting a 5-carbon chain, I'm going to put a 4-carbon chain and see what I can do. Put a 4-carbon chain. I'll put the 5th carbon off the center somewhere. Now I got to decide, okay, where's my double bond going to go? Because I have to have a double bond here. Let's try it like off the end at first. Okay. And again, I'm just starting with the simplest option and moving up as we go. Fill up everything else with hydrogen. Make sure we did it right. So 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens, just like I'm supposed to have. Let's name this one. So we've got a long carbon chain. So I got to have, okay, I got a 4-carbon chain. All right, I see the name for this. So this is butene, because there's a double bond, butene. 4 carbons is the longest chain. and the double bond is on the first carbon, so 1-butene, but then I have to put the name of the branch first. 1, 2, 3-methyl, 1-butene. 3-methyl, 1-butene. Yowza! Now I'm going to do, I can't move the branch anymore. Can't really do that. So I'm going to see if I can't figure out moving the double bond. I'm going to do 4-carbon chain. Instead of putting the double bond in the beginning, I'm going to put the double bond in the middle. I'm going to keep the branch where it is. And then I'm going to go to filling up everything with hydrogen. Now this carbon chain is still 4 long. So we've got but is our parent carbon prefix. Ene, because there's a double bond in there. Then we got a number where the double bond is. This is actually on the second carbon. And so the chain gets named last, and the chain is on the second carbon, and it's a methyl, so it's 2-methyl, 2-butene. Now, I'm going to stop here and say, challenge. Can you figure out another formula for C5H10, the fifth isomer? C5H10. That's your double bonus super challenge. Bottom of the page. Nope. Okay. Aromatic hydrocarbons, they're not on the Regents exam. Aliphatic meant long chains. Aromatic means circles. Okay, you're not really going to be responsible for naming these. When we do name them in our practice, we put the prefix cyclo in for circle. So instead of calling this stuff benzene, we would call that cyclohexane. Why? Because there's 1, 2, 3, 4, 5, 6 carbons in a circle. So hexene, for the fact that there's triple bonds. Oh, haha, I got it. I'll show you why we call this benzene. So hex is the prefix. There's 3 double bonds in here, so that'd be triene. And then it's in a circle, so this would be like cyclo. Let's see, 1, 3, 5. So 1, 3, 5, cyclohexatriene. 1,3,5 cyclohexatriene. Well, that's why we just shortened it to benzene. But that's why we're not going to do that on the Regents, because that's like next gen, next level stuff. We just want to work with straight chains mostly. So now at this point, you should have the basic definition of what an isomer is. It's 2 different molecules that have the same chemical formula. Identify different ways to connect carbon atoms and draw structural isomers of pentene. We did 4 together. I challenged you to do the 5th one. So practice packet, we got a couple page for isomers on 11 and 12. And remember, these things are like Lego kits. All right, everybody gets the same Lego kit. Not everybody makes the same castle, right? You might use all the same pieces, but my castle's got a different shape and look than yours. They're made out of the same stuff, but they're arranged differently. That is the core definition of what an isomer is. So thanks for watching. Talk to you later.